Say you're an industrial engineer employed by the amusement park Duff Gardens to model the waiting time of a particular attraction. You're less interested in the mean waiting time of parkgoers and more interested in the variability of waiting time. The standard deviation of waiting time for the attraction at a particular time of the day is 2.5 minutes, a number you consider to be too high. You make a few changes to the queue layout, and then you collect the waiting time of 85 randomly chosen parkgoers and find the standard deviation to then be 1.75. With 95% confidence, did the changes improve the variability of waiting time for the ride? Okay, so let's take a look at our hypotheses. Okay, we want to know, is the variability improved? Okay, improved means less. If we reduce variability, that's a good thing. That's improved variability. Less than would have to be in the alternative statement because it's not an equality statement. Okay, so is the standard deviation improved upon from the previously set, let's just say, hypothesized proportion that was, or pardon me, hypothesized standard deviation that was previously determined? Standard deviation was 2.5, so the variance would be 2.5 squared. Have we improved upon this previous standard deviation of 2.5? Or is it the same as it's always been, or higher? Okay, so those two are contradictory statements. Equality must be in the null, and we want to know improvement, which is strictly less than. Okay, so we go out, we collect a sample of size n equals 85, and we find that the standard deviation for that sample of size 85 parkgoers, the standard deviation of the waiting time is 1.75 minutes. Okay? And so we want to calculate a test statistic here, and we want to draw conclusions with some amount of confidence. Okay? And that amount of confidence is 95%. So alpha is 0.05. Okay? So our test statistic, our chi-square test statistic, is n minus 1 times s squared over the hypothesized value, sigma naught squared. That is 85 minus 1 times 1.75 squared divided by the hypothesized value, 2.5 squared. Okay? Whenever we work that out, we get a value of 41.16. Okay? So let's say we want to use the critical value approach first. Okay? Critical value approach first, we've got a lower tail test. So here's our chi-square distribution with degrees of freedom 84. 85 minus 1 is 84. And we want all of our alpha to be down here, 0.05. Okay? So we go look up a value associated with 0.95 in the upper tail. 1 minus alpha is 0.95. That's how much is in the upper tail above this value. Okay? But for our chi-square table, we don't have 84 degrees of freedom exactly. Okay? To be a little more conservative, we can round down to degrees of freedom 80. So that's what we're going to do. We're going to estimate this value with degrees of freedom 80. And if we do that for degrees of freedom 80, we get a value of 60.3915. 60.3915. Okay? So here is our test statistic. It is 41.16. That lies right here. Okay? It lies in the rejection region. So we would reject the null and conclude that the new layout, the new queue layout, the changes that we implemented, did in fact reduce the variability of waiting time with 95% confidence. Okay? We could also use Excel. If we're not satisfied with rounding down from 84 to 80, we could use Excel. And that function is, let's do that here. That's the chi-square dot inverse, INV function. Okay? And what it wants is the right tail. This is the chi-square dot inverse dot RT function. Chi-square dot inverse dot RT function. That gives us the upper tail, the right tail probability, or we input the right tail probability, and it gives us a value on the axis. So it wants the right tail probability for a particular degrees of freedom, and that's it. Okay? So we want to input this in as chi-square dot inverse dot right tail, and we want the upper tail probability 0.95, and we want it for degrees of freedom 84 exactly. We don't want to estimate down to 80. We want 84 degrees of freedom exactly, and if we do that, we get a value of 63.876. 63.876. So it's a little bit different than this. Okay, it doesn't change our answer. We're still going to reject the null, but it does give a little more accurate depiction of what this critical value would be. And who knows, for certain cases, that could make a difference in how we draw a conclusion. Okay, so that's the critical value approach, where we estimate the degrees of freedom with 80, or we find it exactly, degrees of freedom 84, using Excel. Now, let's take a look at the p-value approach. Okay, we want the p-value in the lower tail below 41.16. So here is chi-square with 84 degrees of freedom. Here's 41.16. This is not drawn to scale. We want that area. That is the p-value. That is the p-value. Okay? So if we use the table, and if we're going to use the table, we have to use degrees of freedom 80, we'll have to bound the p-value. The smallest chi-square value that we have in the table is this. It is at 51.1720 chi-square for 80 degrees of freedom. That's the smallest value on the axis that we get, and that's got a lower tail area of 0.005. Okay? That's the best we can do. So we know that the p-value is smaller than 0.005 because 41.14 lies somewhere to the left. That must mean that the area below this is smaller than 0.005. Okay? So with the table, the best we can do is this. Or we can use Excel. Well, by the way, so let's just draw conclusions based on this thing. This is a very small p-value, much smaller than alpha of 0.05, much smaller than any alpha we would ever choose. Since the p-value is smaller than alpha, we reject the null and conclude that the variability has decreased with our implemented changes. Or we could use Excel. Okay? So with Excel, we would use the chi-square dot dist function. Chi-square dot dist function. And it reads in the value on the axis for a particular degrees of freedom and whether or not this is a cumulative distribution. Okay? Cumulative. Okay? So how we would read this in would be with chi-square dist dot dist. Okay? The axis value is 41.14. The degrees of freedom, exactly 84, okay, because we don't want to estimate this degrees of freedom. And we want the cumulative distribution. So we're going to say true for the cumulative distribution. Okay? And if we do that, if we enter this into Excel, we'll get 2.2628 times 10 to the minus 5. Okay? So that is 4 zeros. Let's just write this out. That is 0.123422628. Okay? Pretty small number. It's indeed smaller than 0.005. Okay? Much smaller, much smaller than any alpha we would ever choose. We're going to reject the null if the p-value is this small. And we're going to conclude that the variability of waiting time did indeed decrease with the changes that we implemented. Okay? So we've got the critical value approach where we have to round down from 84 to 80. We've got the critical value approach to find the critical value when indeed there are 84 degrees of freedom using Excel. We get the p-value approach whenever we use 80 degrees of freedom and use the table. Okay, we can bound that p-value. Or we've got the critical value, we get the p-value approach when we use Excel. We can specify the degrees of freedom exactly, and we don't have to round down, or we don't have to bound our p-value. We can find it exactly. Okay, so all of these we can implement using the table, using Excel, critical value, p-value, all for a test of hypotheses for a population variance.